Late 19th century scientists wondered how hot objects glow, and I wonder if I try to heat an aluminium cavity, will people watch my video? I mean, will it glow? Wait, why cavity? Hear me out for a minute or two, okay? When light falls on a regular object like a box, some of it gets absorbed and some gets reflected. Now imagine a box B which absorbs even more light and reflects even less. Is it possible to have a box that absorbs all the light? Technically not, but scientists, being scientists, found a workaround and gave it a name: blackbody. The rule for a blackbody is simple: any light that enters must get lost inside forever. So back in 1859, a scientist named Kirchhoff had a clever idea. Take a hollow box, make a tiny hole in it, and shine light into the hole. What happens? The light enters, bounces off the inner walls again and again, and with each bounce, a little more gets absorbed, until eventually all the light is trapped inside. But why bother? Why not just paint the box black and call it a day? Well, think about it. You can see a black object, right? That's because even though it absorbs most of the light that hits it, it still reflects some. That leftover reflection is what your eyes catch. A true black body does not reflect anything. Total absorption, total darkness. So, I decided to try making one at home. I mean, how hard can it be, right? I had some aluminium foil containers. At first, I tried to make something like this shape and put this bigger one over it, but there were a lot of technical problems. So I figured you can put one container over the other and make something like this. The final product looks like this. Just seal the edges by folding it and pressing the foil so that the light cannot escape. Why did I choose the metal? Why did I choose a metal? Why not this perfectly fine cardboard box? A cardboard box with a hole should technically work the same, but your girl right here is ambitious. I'm planning to heat it and try to see the radiation coming out of that cavity. Cardboard and heat? Not a good combination. But wait a second. Why heat? Because I just said that a perfectly fine black body must be a perfect absorber, right? Yes, but that's just one piece of the puzzle. A black body is a perfect emitter as well. Forget about the absorption for a second. This box has some temperature, right? That means the electrons in this box are constantly vibrating. What does an oscillating charge produce? Electromagnetic radiation. And it has nothing to do with the absorption. Every object radiates. The hotter it gets, the more it radiates. This radiation depends on the temperature, material texture. For a perfect black body, the radiation is 100% efficient. Welcome to my advanced laboratory where I have this high-tech burning machine. Now, as we heat this, both the outside and the inside are getting hot. Outside radiation will be just the thermal radiation. Only the radiation coming out from the cavity through the hole is considered blackbody radiation. And a blackbody's emission depends only on its temperature, not the material, not the texture. Let me explain. When the foil heats up, the electrons vibrate and emit electromagnetic waves. Inside the cavity, these waves bounce around, forming standing waves. At equilibrium, this depends only on temperature, not on the material, and these standing waves come out as blackbody radiation. Honestly, I just feel dumb at this point. I imagined like when we burn a safety pin, it starts glowing red hot within minutes. And here I am wasting so much gas. This cylinder costs like rupees 850. And here I was dreaming of little rainbow popping out of the hole. Okay, maybe not a full rainbow, but at least some cool colors one by one. You see, blackbody radiates all the frequencies of light all the time. Look at this peak, which shows the type of frequency that is being radiated maximally. At room temperature, this curve is like this. Maximum radiation is in the infrared zone. That's why we do not see each other radiate visible light. If the temperature is high, the curve shifts and the peak starts to go towards the visible light, and we can see the radiation. Still nothing. Pitch black inside. Is it even possible to get visible radiation at room temperature? Well, Mr. Wayne gave us a formula. Suppose we want to see red light. The wavelength of red light is 700 nanometer. So just by basic math, we get the temperature, which is equal to the 4140 Kelvin. Now let's ask ChatGPT, how hot is an LPG gas oven? Or a gas stove for that matter. It says, inner cone flames can reach approximately 2000 degrees Celsius maximum, which is pretty good, but that's just a flame. Getting my aluminium cavity to actually reach that temperature? There goes all the hard work down the gas line. Also, if you could reach around 200K, you will see a faint red glow. The peak of or the maximum radiation is still in the infrared region. And if you want to see the blue light, you are welcome to stay with me when your mom kicks you out. Thanks for sticking with me through this mildly embarrassing journey. I hope you enjoyed the ride.